here. Links. This one, right? Let's back to the chat. And yeah, okay. Let's see. Is it there? Yeah, no. Doesn't sound very good. Oh. Okay, all right. Very good.
Because it picked up the system line.
That's probably it, yeah. Okay. All right, guys, we're going to start. So today we're going to talk about randomness in scientific computing. And we'll discuss a little bit of why we want randomness, because it seems a little bit strange and counterintuitive. If you want to calculate something that we add noise to it, we want to suppress it, don't we? But we'll see that it can be very useful. Then we'll show how to make randomness. Again, something that you wouldn't think you'd have to do, but you have to do it. And we can't, turns out, so we have to fake it. We'll show you how to do that. And then we'll go into a few applications that will make it hopefully clear that this randomness is useful. And these are all gathered under the sort of umbrella term of Monte Carlo methods. So why randomness? Well, sometimes you just want to simulate something that is inherently random, that has some noise to it. You might be describing something on a mesoscopic or molecular level that exhibits Brownian motion. You might be looking at a circuit that has Nyquist noise or any kind of noise. And so on this level of the description, this noise is real and it's random and it's just part of the system. So if you're simulating it, you have to add that noise. Sometimes, however, we add noise to help things like performing averages in systems with many degrees of freedom. We kind of alluded to that also when we did the minimization. So if you're doing anything from statistical physics, if you're doing an average, canonical average or anything like that, but even if you're doing path interval calculations, you're basically performing a big average over a huge dimensional space. And going randomly through that space in some sort of reasonable way can be much faster than trying to come up with a way to do it exactly or to do it on a regular grid. So this randomness can actually help you cover more of your integral. Another reason you might have randomness is that you want to test some sort of statistical model. So you have a model, you want to add some noise, see what happens. Or maybe you have a method to get rid of noise. Well, how do you test that method? Well, you have to create some noise, right? So for tests, this can be very useful as well. So let's assume for a moment that we do want some randomness. How do we get it? Well, we could turn to some real random stuff. Lava lamps, radioactive decay, various quantum processes, atmospheric noise, random computer hardware noise, or the way you've typed your stuff into the keyboard, all of that can and has been used to create randomness. Unfortunately, this is generally a very slow process, especially the lava lamps you can imagine, but even radioactive decay or random noise. At some point, you sort of run out of random numbers. You've exhausted the randomness, and it's not fast enough for some of the things that you might want to do. So if you're simulating something that has inherent noise, you would have to have a real physical system that has as much noise as that, which almost defeats the purpose of simulating it. Okay. Another thing that is hard or difficult with these real random numbers is that it can be difficult to know what the distribution is of these numbers, and this might influence especially your numerical calculations. Where these kind of things are used are in things like encryption and security, where you don't need a lot of random numbers, but you need them to be very, very random so that the key that you get can't be just guessed by a third party. But that's not what we're doing here. So what we'll come up with are pseudo random number generators. They're not really random in various ways. They are deterministic. There's an algorithm that produces a number, and then the next number, and then the next number, in such a way that they seem random. Now, such an algorithm, since it's run by the computer, must be deterministic. It might start from one of the true random numbers, but it's still deterministic. So that can pose a problem. And that's what we're going to look at next. Because all we really need is for it to act random. So it has to be fair and uncorrelated. So this is kind of the general way that these pseudo random number generators work. Since it has to be a recipe that creates one number after another, the previous number has to somehow depend on, or the next number has to depend on the state of the previous number. So what happens is that these things are like machines that are in some sort of state. You initialize them, and then they produce a number from this state, and the state progresses to whatever the next state is. So the numbers in the state don't necessarily have to be the same. Okay, there could be some complex machinery that makes sure it's random. It's the number that comes out one at a time that needs to seem random, and the machinery inside can be as deterministic as we need it to be. So the state is deterministic. The random numbers that it produces should seem to be independent, identically distributed according to some predefined distribution. So the distribution has to be satisfied, and they have to be independent. If that's true, we're fine. We can use these numbers for random calculations, but it has to be true. And the fact that the state behaves deterministically is a bit of an issue. So it depends a lot on the details of how these states are advanced. And so one of the things that you will have to do is test that your random numbers are good enough. So let's look at an example that is extremely simple, a little bit too simple. We're going to try and simulate coin tosses. And in this case, +1 will be a head and -1 will be a tail, just an integer. And this is one of those little state machines. We've made it into a class, but it's pretty simple. There's a state. This is just an unsigned integer. This is just an integer. And I started off, I seeded with some value for that. And every time I want to know a number, I call this toss function. And what it does, it just increases the state by 1. Well, that would make this seed go up to large numbers. I want to get out of that, a 1 or a -1, so I just take the modulus of the state with 2, so whether it's even or odd, and then I times 2, subtract that from 1, means that this number that I return is always plus or minus 1, right? So the state changes. From the state, I derive a number, and each time I get it back, I get a different number. So if I wanted to use that, I just define an instance of this Faircoin class. I started off with a seed. I really like the seed 13 because randomness and being unlucky just goes well together. And then 20 times, I toss the coin and I print out what it is. Anybody have a guess what this gives? It gives a sequence of -1s and 1s, right? Okay. Good. So what we want is for this to be fair, a fair coin. I've tentatively called it fair coin. It's money up and down, heads and tails, and independent. So how do we test this? How do we test for randomness? Well, I'll look at two tests in particular. One that is good for fairness, to test fairness. And you can just make a histogram, or in other words, just count how many times do I get the value x in my samples xi. So xi are the samples. I goes from 1 to n. In this case, they're all plus or minus 1. And then this x subscript here is also plus or minus 1. So C1 is how many times I get 1. C minus 1 is how many times I get minus 1. So that's, and then we'll test, if I look at those numbers, they should all be equal, right? They should get an equal number of heads and tails for it to be fair. I also want it to be independent, and for that we have to do a little bit more work. So independence means that the next sample doesn't depend on the previous one, because each time I flip a coin, it should be independent, right? That is. So I'm going to look at this particular quantity Cj, which is the correlation between coin tosses, the coin toss I and coin toss I plus 1, and then just average that over all of them. So I take my result at the ith case and the I plus jth case, and I multiply them and average that. That gives me a correlation. If things are independent, then if j is bigger than 0, this correlation should be of the order 1 over square root n. The 1 over square root n just comes from the fact that we have a finite number of samples, and so it won't be exactly 0. It will only be 0 in the limit that we draw it infinitely many times. In this case, I've taken it to be periodic. You could do different patches or different ways, but for this purpose, let's just say it's periodic. Typically, you wouldn't, but it makes the plots easier. It shouldn't actually matter if they're truly independent. Periodic or not periodic doesn't really matter. Okay, so let's test them for n equals 20. This is my histogram. I get 10 values of -1 and 10 for 1. Woohoo! Right? So this is an absolutely fair coin. That's great. It's actually designed to do it this well. So let's see how it does for independence. So I'm going to plot this Cj as a function of j. So j is the time delay between subsequent throws. And this is what I get. So what I want it to be is of the order of 1 over square root 20. I'll let you figure out what it is, but it definitely isn't 1. And this jumps up from 1 to -1, 1 to -1, 1 to -1. Why do you think that is? Look at the code one more time. If you go through this carefully, since the state is increased by 1 each time, all that matters whether it's what it returns is whether the state is even or odd. And that just alternates if I keep increasing it by 1. So I get heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. That is very fair, but it is definitely not independent, right? If I've had heads, I know 100% sure that the next one is tails. This is not independence. Okay, so although it's fair and it follows the distribution that I wanted it to have, it's not a good random number generator. And that's what this oscillation between 1 and -1 shows. Okay, very bad. This is not a good way to do it. Even if it's fair, it's not good. So let's just try some stuff. Let's just randomly make some changes in how we update the state. So I'm calling the sine function on state plus 1 and multiply it by 100 and add. I do this for no particular reason, okay? I just guessed this. I'm going, this is going to be more complicated. All right, so let's just do it and hope for the best. It's not how you're going to design one, but it's just to make the point. So we can try again with 20 numbers. And okay, it's not as fair. I think this is probably 11 and 9, but that's pretty close. I mean, it's not as good, but it shouldn't be perfect. If it was perfect, I had this problem of repetitions. And then I can do my correlation, and well, might be better. It starts at 1, that is normal, and then this, oh, maybe that's not so bad. Maybe that's just noise. But it's hard to know, right? We basically don't have enough samples to know if this is good or bad. So let's increase our number of samples. A few very annoying things happen. First, way more heads than tails. So that's not good. It's not balanced, right? But maybe the independence is good and we can sort of skew it after the fact. Actually, no. So this one's also horrible. It seems to go down a little bit and then go up and has all kinds of periodicity in it. This is not uncorrelated random stuff. This is again bad. So the moral of this story is don't try to make these things yourself. Okay? We want them to be uniform, unpredictable, reproducible, which is why we have a state that is deterministic. And reproducibility really is there for if you're testing your code and it does something weird, when you're debugging and the next time your random numbers are different, that weirdness might not occur. So you want things reproducible, even if they're random. That sounds funny. Generate quickly, that's why we do them, and have a long period. So in this case, these, you can kind of see that there is a period somehow, and even in between that, there's periods. We want that to be as long as possible. In other words, at some point, you're going to exhaust the number of numbers that are even possible, so that's your longest possible period. But most random numbers have some period below that. If that's 10 to the 20th, and that's how many numbers you can draw, you should know this, but you're going to be safe. Well, with the distribution that I asked them to have. That's right, yeah. That's right.
There are cases where variables are
uncorrelated, but not independent. Can you give an example? Well, okay. This is one measure. If this one shows correlation, there's dependence. So it's a test, but it's not the only conclusive test. That's right. Yeah. So now it used to be that there weren't many good random number generators around, and people didn't necessarily know this, but you'd get the standard C random number, which is just called RAND, was really not particularly good, and people that used that might have gotten wrong results just because correlations would have crept up in their calculations that they weren't counting on. But times have moved on, and these days the C++11 standard has random numbers that are very, 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 very good. They've learned from scientists what are the good ones. So we're going to use those. So we can rewrite our fair coin using the random header, which is just C++11. And it doesn't look much more complicated. It's the same idea. The only thing here is that our state is replaced by two things, an engine and a distribution. So the random library makes a distinction between generating the numbers and then making them transform into a distribution that you want, which is fine. That's how it is. This means that you could change the distribution and still use the same random number. You could add a distribution and not have to re-implement the randomness of it. So these are good things. The engine is the one that gets this random seed, that gets initialized. It has that state. But then uniform can be given this engine and return a number that is distributed properly. In this case, I still have this state thing, but it should be an internal variable. There should have been an int in front of here. So it gets something from the uniform distribution from 0 to 1, which is actually integer, so it's 0 or 1. I hope I did that right. I think so. 0 or 1. And so I didn't really have to do this percentage stuff. I could just, but in any case, it uses this uniform distribution of zeros and ones and then transforms it into -1 and 1 because that's what I asked it to do. There's probably a way to do it in one fell swoop with another distribution, but this way it looked more like the fair point. So let's see how this one does. Note that I'm using the default random engine, which isn't strictly defined what it is, but it's one of the ones from the C++11 ones. You can be more specific, and we'll go into what are some good ones later. But fairness. So another 200 samples, 110 and 90. It's reasonably fair. Actually, this is kind of what you should expect. There should be some unevenness for such a small sample size. So let's look at independence. That's nice. Starts at 1, at 0, and then very quickly goes to something that sort of fluctuates around 1 over the square root of 200, or something in that order of magnitude. That's what independence should look like. Right? That's what an uncorrelated signal should look like. Okay? So whenever somebody hands you a random number generator and says, look, this one's really good. We've been using it for 50 years in our group. At least perform tests like these to show them that they're probably wrong. If it's been used for 50 years, they're probably wrong. Okay, so what are some good and bad ones? I'm just mentioning a few. You can look up in the C++ documentation which ones it supports. I know it does the Mersenne twister. There's lagged Fibonacci ones. I'm not quite sure if they're C++, but in any case, they're good ones. Well generators are pretty good. Not so good ones is anything from numerical recipes. They're slow and they're kind of correlated or have short periods. And they can have spectacular failures of some of these tests. Definitely don't do anything that is standard Unix. Rand, even drand 48, unless you're drawing 3 random numbers, I think you should just stop. Very correlated. As I said, we don't have to worry about it much anymore. We will have to say when you publish a paper what random number generator you use. If you're suspicious still, because you can always be suspicious, the nice thing is you can just swap one random number generator for another and see if your results don't change in any statistically significant way. That's the least way that you should test your random numbers. You computed something with one random number generator, you're not quite sure of the results, test it with another one. If it gives wildly different results, one of them is probably wrong. Some other tests for randomness, just for completeness, one could look at moments. So if you know the distribution, you could see if the other ones are good. This only concerns the distribution, not the independence. So I'm not much in favor of doing this once if you don't know the rest. But you can do some other tests. You can look at random points, see how much they're separated, and if they're random between 0 and 1 continuously, they should follow a Poisson distribution. You can try and randomly sort numbers and see if you get all 120 ways. You can play 200,000 games of a dice game like craps and see if things are balanced, etc., etc., etc. If you want a nice tool or a test suite, NIST has one in this reference. There's many games you can play to see what are good and bad random numbers. So that's random numbers. So now we have good ones. I kind of alluded to why we want them. I'm going to try and make that a little bit more clear by talking about Monte Carlo. So Monte Carlo analysis or simulations or methods are really just a common denominator for any techniques that use randomness. And so you kind of can distinguish 3 categories. One where the dynamics is deterministic, you just add randomness to see how it affects things. So sort of a robustness analysis if you want. You might want to generate samples from a given distribution, one that's complicated and it's hard to deal with the closed form. And then often if that's what you want, you might want to do things like evaluate the averages under that distribution function. So this covers also all of statistical physics and a good bit of path integrals. It's kind of in this form, especially if you discretize. And so that's where you'll find applications of Monte Carlo. If X is highly dimensional, these integrals are problematic, and so Monte Carlo is probably your only option. All of these, of course, depend mathematically on having a valid, good random number generator. Okay. So let's look at a few examples. It's going to be fun. Investment returns. I just want to make sure you understand that this is actually used widely and also outside of physics and academia. So there's this index called the S&P 500 that is a collection of stocks, essentially. And you can invest in it, or you can buy parts of it and then get a return out of it. And this return fluctuates. So let's say we look at this time period between 94 and 2004. It fluctuates somewhere between 10.6 and 18.1%. So that's the annual return, right? So that's how much you grow per year. But then the next year, of course, you grow on top of that. or maybe if it's really bad, you shrink. So the question is, suppose that I know this, and suppose I assume a standard deviation of 18%, and I started with $100. What can happen, right? What is the likely scenario? What's the average return on my investment? But also, what is the likelihood that I lose everything, or what's the likelihood that I make $1 million? So this is where I can use randomness, because I can do this process where I pick a return from this with this distribution, and then just apply it. And I just do that year after year after year, and then I do it 500 times, and I see what's the distribution of my returns. Each time I pick a different annual return from each of the years. So it's sort of a backwards prediction. So if you do that, you get something like this, just so you... I had numbers. Oh, yeah, they are on the other one. So I started with $100. I invested. The average is about just under 200. Rather modest, right? But that's... there are people that made, or there might have been people that made like almost $1,000 from that $100, so a tenfold return, but not many. And there are some that lost pretty much everything. Luckily, it was only $100, and hopefully they could spare this. But and so getting this distribution in any other way is kind of tough to do, right? There is math that can help you with this in this case, but if you make your model more complicated and you don't just consider this as one stock, or this can get complex. So this is a simulation that can be used for risk assessment, and this is actually used. A bit more closer to, I guess, our kind of modeling, traffic. I wish they did more of this in Toronto and figure out how bad our roads are congested, but traffic flow. So let's look at something more simpler than Toronto. There's a 1D toy model of traffic flow. You can get traffic light behavior. So we have one road, it's kind of long, and toy cars are on it. It's discretized, so one car can occupy one spot and it can hop to the next spot. It has a velocity, so the velocity actually determines how many spots it hops each time. And this is sort of the rules of the road, or of behavior of drivers in this model. If your velocity is less than the maximum, you speed up by 1, because everybody tries to go at the speed limit. If there's a car in front of you that you would hit if you did that speed up, essentially it says you're not going to do that. You're going to reduce your speed so that you don't hit the car. And here comes the randomness. If you're going with any kind of speed, there's a randomness that you might break. You might see something, you might slow down, you might just temporarily, for whatever reason, every now and then you reduce your velocity by 1 with some probability. And then every time, since your velocity is v, every time step your car moves ahead by v steps. So basically we have these 4 rules. The velocity increases unless you're at the maximum. The velocity is either the velocity or that which is necessary not to bump into the next car. Every now and then you're either standing still or you reduce your speed by 1. So you're not going backwards. It's a one-way street. And then you move ahead. So what happens if we solve this? And so only step 3 has this probability. Without this probability, you're either completely deadlocked or it's moving along just fine. But with the probability, you can get things like this. So I should explain this plot. Here's the position and time. So at one given time, every dot is a car. And so if they're moving along nicely, you get these nice streamlines. This is the maximum velocity. It's all moving along very nicely. But every now and then, just by randomness, cars are so close together that they stop. So they're not moving along. But what is nice about this, and this is actually, you can observe this in real life. So we've got the beginning of a traffic jam here. And what happens is this sort of seems to travel backwards. So it grows, but not only does it grow, the cars that were in front are already out of it, and it sort of grows backwards. So some accident happened here, say, or somebody just stepped on the brakes too abruptly, that caused And that is just by chance. This caused this traffic jam. But by the time these guys are out of the traffic jam, there's nothing to be seen anymore. If you've had this experience, but you're in a traffic jam, you're stuck forever, then finally it dissolves, and it seems like there was nothing happening at all. Why were we stuck? Well, we'll never know, because it happened, first of all, further away. So at some point, you might see that car at the side of the road. That was the car. And so this is kind of what happens. So it's a nice way to show that kind of behavior of traffic flow. Obviously, you can generalize this. Without the randomness, this doesn't really happen, because either everything is too close together, sort of stuck, and you also can never get resolved. Without the randomness, you also can't resolve things, right? So it's one application. Now I want to go back to something a little more practical. I said that we have randomness here because randomly we hit the brakes or don't step on the gas as hard. With probability P, we reduce our velocity. But how do we do that every time step? How do we reduce something with probability P? In a computer, we do it or we don't do it, right? So we got to flip a coin or something, but with the probability P. So this is how you use it, and this goes into the heart of a lot of these stochastic simulations. You're going to draw a number R from a random number generator that has a distribution that's uniform between 0 and 1, continuous, not just the integer values. Now, we're going to use that for any value I choose between 0 and 1, the chance that R lies to the left of it, in other words, is smaller than it, is P itself. Because it's uniform, right? So I'd land between 0 and P a fraction P of the time. I land in the rest a fraction 1 minus P at the time. So if I want to do something with probability P, I can check if this random number I just drew is less than P. And if so, I accept this move. I will actually reduce the velocity. So we say we accept the move. If it's greater than P, we leave V as is. We don't do it. So this is how we implement doing something with a certain probability. Make sense? All right. And then finally, something a little bit more along the lines of physics. You can use this, use Monte Carlo methods for molecular motion too. So consider doing this. I have a set of molecules or atoms or what have you, and I'm going to randomly perturb their positions. Or maybe just take one of the atoms and move them about a bit. Randomly, in a random direction with some way. I'm going to calculate the new energy of the system. So the energy in the system, last lecture we talked about a couple of force potentials that were there. One of them was Lennard-Jones. We could think of having Lennard-Jones potentials. We sum them all, we move the particles, we sum them again, and then we follow this rule that if the energy of the system goes down, we're happy with that new situation. And you could imagine that maybe we're trying to find a minimum. That's actually not the case. The second criteria is that if the energy goes up when we move this one particle, we will only accept that with a certain probability given by the exponent of minus delta E over T, where T is the temperature. So this is that same mechanism that I just said. With probability, with certain probability, we accept this. So we draw this R, this random number that is needed for nothing else but to implement this doing something with a certain probability. And we see if it's less than that. And if it is, we accept it. So every now and then, we accept changes of the configuration that increase the energy. We're not looking for the minimum here. What we're looking for is an equilibrium of this system at temperature T. And so you can show that if you do this, you get an equilibrated system, you do this long enough, at temperature T. You can imagine that if T were 0, right? That's 0 Kelvin, then this becomes infinite, this becomes 1. I will never, saying this one, or should it become 0? Okay. If it's 0, I should only accept energies that go down. So at absolute zero, I should get the lowest energy. Whereas anything else, every now and then, I should get a kick up. I should be able to go at higher temperatures, because the nature of a canonical equilibrium at a certain temperature is that you have a distribution of energies around a given energy, not the lowest energy, which is often zero. Okay? So you do this every time step for each of the molecules and for all time steps, and then you slowly get your molecule to relax to its native state at that temperature. So this can be useful if you don't know what that is, what that configuration at temperature T is. And just to show kind of what that looks like, it's not a very good movie. I didn't have time to make a really nice one, but imagine these are our molecules, and we just sort of randomly put them together. This might be what happens. I'm not impressed by this. It's cute. I'm not impressed. It doesn't look like it really anything behaves like that, right? If these were real molecules, this is not what they would be doing. If these were stars, it would definitely not be what they were doing. Right. I can apply the methods, like we saw last lecture. I can apply these n-body methods either to stars or to atoms. The formalism shouldn't matter. But we would not be happy. Like if I were an astrophysicist, I would not be happy with this, right? Unless these are some sort of massive asteroids in a gaseous substance, and maybe that gas we didn't put in explicitly, but it's moving my particles around a little bit randomly. If it's in some sort of medium, if these are Brownian particles, they're in a liquid, we don't see the liquid, you just keep track of the Brownian particles, then this would be reasonable. If I could look in a microscope and I see this, I'm going, yeah, sure. So, go back to the... But this comes with a caveat. This isn't real dynamics. I want you to know this. You'll see many papers that don't even question that this is dynamics. The authors know what they're doing, and it's a model. But at first glance, people will sell you molecular or Monte Carlo dynamics as if it's dynamics. It's not, okay? Sometimes it's a good approximation, but sometimes it definitely isn't. And stars is definitely one case where it isn't. It is a very good way to study equilibrium. Okay? So if you have a gas or a liquid or something that sort of will become, will get to an equilibrium state at a certain temperature, perfectly good. If you want to know what a biomolecule looks like, what its configuration is embedded in that medium at a certain temperature, again, very good. But you don't really care how it gets to its equilibrium. You don't care as much about the dynamics. Okay? Every now and then, it might be appropriate. Small particles immersed in a liquid of smaller particles. Sometimes this isn't too bad. Usually you have to have extra effects in that model anyway to make it really well, but then... but now, it's not bad that it's not a real dynamics. It's artificial. Right? It's not real. We only do it to get our integrals. Which means we can make things worse. We can make dynamics that's even more artificial. We could have stars go straight through each other, as long as we have some way of undoing that bias, if we want to know the average configuration of a galaxy. I don't know. Doesn't matter how I explore that phase space. And so if there's a way that I can devise to explore the parts of phase space that I'm interested in by doing an artificial dynamics, fine. It doesn't matter. It's not dynamics anyway. We're after the statistics of these systems. So there's a whole set of possible tweaks you can do. I can't even begin to list them to open up faster convergence using Monte Carlo. I was going to put in, but went too far, a similar application to quantum mechanics and path integrals, which are also, since it's an integral, it basically look like an average. And so you can come up with artificial dynamics of your paths. They don't do anything. Their paths are the paths and they're summed, right? You have dynamics of your paths, and that, although it doesn't look like anything that behaves well, can give you proper estimates for what these quantum mechanical property should be. All right. Questions? Randomness is nice. Make sure you have the right kind of randomness, test it. And then there's a whole bunch of modeling you can do, all kinds of different applications of this stuff. So that's the end of section 2 of 3 sections of this. So what have we learned? Hopefully. We've looked at root finding and minimization, so we saw how to use that. We looked extensively at linear algebra. We looked at fast discrete Fourier transforms. We saw how they apply to all kinds of things, numerical solutions to ODEs, where they again apply, and random numbers. So that was this section. We weren't concerned too much with modular programming because it was about the techniques, but those things are still important. It's just if you're looking at one technique at a time, and not as it's critical to get your feet wet. So next week, what we'll do is we'll start parallel processing. We'll look at how to not just use these libraries that are already optimized, but how to make the most of all the cores that are either already in your laptop or are on the supercomputer in Scilab. So we're going to be using Scilab more starting next week. Yeah, that's where we're at. Thank you.
Time for questions.
Yeah, good.
So I got it finished in CA, but wasn't really satisfied with one part of it, which was how to do the power spectrum calculation. Is there a smart way to do that with C-Blast? I just did it taking the norms.
That's the way. So C-Blast is tailored to linear algebra, and there's no linear algebra operation that corresponds to taking the norm of all elements. So it's kind of outside of its scope. There are, like, if you are using a library like the MKL, then they have routines for that, but it's not part of the linear algebra part.
Clearly vectorizable.
Exactly.
Much smarter ways.
That's right. Chances are, if you just have a simple loop, the compiler might vectorize it for you, but because it is simple, yeah. So, but yeah, there are, but yeah, it falls out of the scope of linear algebra as such, and that's why it's not. I mean, it's annoying because it's obviously an often used case, but oh well. All right. Okay, this one can go. Let me switch this one off too.